Hello, in this tutorial we are going to go through the process of conducting response history analysis using IIDAP. So we will go ahead and open IIDAP. Once IIDAP is open, we'll go ahead and start a new project by clicking the New button over here. This will show me a dialog box to select the workspace directory and specify the project name. So I will call this project RHA project. Following this, I need to specify the project units, either kilonewton meter or kip inches. For now, I'll use kilonewton meter for this project, and I will click submit. Now I have this button active for the first step of defining a project, which is defining the SDOF system. I'll go ahead and click Define SDOF. To define an SDOF, you need to specify the four main parameters. This is the mass, the stiffness, the period, and the damping coefficient. For the first three, you need only to specify two of those, and the third will be calculated accordingly. For this project, I will just use the period and the mass. So I will state a mass of 2 tons and a period of 0.8 seconds. Once I define the mass and the period, notice that the stiffness is calculated automatically. For the damping coefficient, I will add a 2% damping coefficient. As an option, you can include P delta effects. To do this, you need to check this checkbox. There are two ways to add P delta effects, either by specifying the gravity weight P and the height H, or by directly specifying the stability coefficient. For this project, I will use a stability coefficient of 0.02. I'll click submit. The second step, once now our SDOF is defined, is to define the system model response. So I'll go ahead and click on this button. Currently, IIDAP offers 6 different system models. We'll go ahead and select the first one and the most simple one, which is the linear elastic system. This system model is defined only by the elastic stiffness, which is in this case, if you look in this figure over here, it's already rotated slightly because we included the P delta effect. You can additionally add a limit on the force or the displacement of these systems by checking this box. For our project, I will not add a limit for either the force or the displacement. So I will go ahead and click submit. The third step is to define the ground motion. So I will go ahead and click on this button. The ground motion module offers you 3 different options. The first one is to import a single record. The second is to import multiple records. The third is to define a harmonic wave. For our project, I will select a single record. For this, I will need to click the Browse button in order to import the file for the ground motion. For this, I can use the support files provided with IIDAP for this purpose. So I will use the sample ground motion El Centro. This file that I just selected contains 2 columns of data. The first column contains the time history. The second column contains the ground acceleration. For this reason, I don't need to specify the time step since it will be automatically computed. If I selected a file that contains only one single column of the ground acceleration, then I will need to specify the time step. I will leave the scaling factor of the ground motion as 1 for now. So I will go ahead and submit. So now the ground motion is defined. If I want to check if my ground motion was imported correctly, you can go ahead and click on the scope button over here. In this window, I can see the acceleration history of the ground motion, as well as the peak ground acceleration highlighted over here. IIDAP also computes the velocity and the displacement history of the ground motion, as well as the Fourier transform. For these other plots, you can select from this pop-up menu or just use the buttons here to go through them. So the velocity history, the displacement history, as well as the Fourier transform. So it seems that my ground motion is imported correctly. So I will close this window. And then we'll go to the final step of defining a project, which is defining the analysis type. So I'll go ahead and click on this button. IIDAP currently has 4 different types of analysis options. We will go with the first one, which is a simple response history analysis using a single ground motion scale factor. I'll go ahead and click next. So now IIDAP tells me that it's ready to run the analysis. So we'll go ahead and run the analysis. But before I do that, if I want to check if everything was defined correctly or if I missed something, you can go here and click on the scope next to the project name. This will show you a window with a summary of the single degree of freedom system properties, the system type, the ground motion, and the analysis type that you defined in this project. So everything seems okay. So I'll close this one and I'll go ahead with running the analysis. When you run the analysis, now you have this notification. This notification tells you that dynamic analysis will be performed using the default integration method, which is the Newmark constant acceleration method, unless the user specify otherwise. If you want to change this or change the time step, you can click on modify integrator. Otherwise, you click OK, proceed. So for now, we will use the default integration method and time step. So I'll go ahead and click proceed. Once I clicked OK, the analysis has been run. And since this is a single ground motion, this process was very fast. And now the analysis is done. And those 2 buttons are now active to view the results or save the results. So if I click on view results, I'm getting several options that I can select from to visualize the response history analysis plots. We'll go through the first one, which is the RHA plots. If I check this box and click view, this will give me this window, which shows the ground motion here, since it's single ground motion, so I have only one option. For the plot type, I can plot the response history of different quantities, including the relative displacement, the relative velocity, the relative acceleration, the absolute acceleration, the pseudo velocity, and the pseudo acceleration, as well as the force spectrum. You can also use those buttons to go through each one of those quantities. For each one, you will see the maximum value highlighted on the plot. If you are interested in one of those plots and you want the data to do additional work on it, you can click on Save Plot Data. In this window, you need to specify the location as well as the name of the text file to save this X and Y data. So I'll close this window for now. You can also look at the force displacement response by clicking View. In this one, you can see in dotted black line, this is the backbone of our system, which is in this case just an elastic slope or a linear slope. In red, you see the response of the system. Again, this is a linear elastic system, so everything is moving on this same line. You can also see animation of the deformation response by checking this box. In this one, you can move through the different ground motions if you already defined multiple ground motions. By clicking play, you will see an animation of the SDUF system with the ground motion moving here, as well as animation of the absolute displacement at the top, mass lumped at the top of the SDUF. You can increase the speed or lower the speed of this animation. You can also pause at a given point or play again. You can also see an animation of the force displacement response. In this case, it's a linear system, so everything is moving on this linear line again. In the last option, you will see a composite animation of both the system as well as the response force displacement synchronized at the same time. If you want to save the summary results for this response history analysis, you can go ahead and click on Save Results. So now it says that results has been saved. So if you go to the location where you define your project, you will find now a new folder called Results and then the name of the project. Inside, you will see a text file containing the project summary. You will also find another file for each ground motion. In this case, it's only one file for one ground motion that contains the response history quantities. This includes the time, the ground acceleration, the relative displacement, relative velocity, relative acceleration, all the way up till the force. You can use this file to import the data to Excel or MATLAB or any other software of choice to do additional work on the data. So right now I will keep all my project definitions, and again I will conduct a response history analysis, but this time using multiple ground motion instead of single ground motion. So I'll go ahead again and define a new ground motion. In this case, I'm using multiple records. For multiple records, you need to browse for the folder containing the multiple records files. So I'll go ahead and click Browse. And I will use the support files that came with IIDAP. So in support files, I have those two folders for ground motion set, far field from the FEMA P695, as well as the ground motion set LMSR, again from the FEMA P695. So I will go ahead and select the ground motion LMSR, this folder. The scale factor, I will leave it as 1. Note here that you can also have an option to add a free vibration at the end of each ground motion. So I can add, for example, let's say 10 seconds at the end of each ground motion as a free vibration. For now, I will not add this. So I will go ahead and click submit. So now the ground motion data are being imported. This might take 10 seconds or so, depending on how many ground motions are being imported. Once the ground motion data has been imported, you will see here the window will close, and then you will see here that the ground motion, multiple ground motions again. Then you can check with the scope to make sure that all the ground motion has been imported correctly. By clicking on the scope, you can see here this is for now all the ground motions that I imported right now. You can browse through the different ground motions as well as the acceleration history, the velocity history, and the Fourier transform for each ground motion. Everything seems okay. Then I can go ahead and run the analysis. Again, I will get the notification regarding the default integration method. So I will go ahead and say proceed. So now the response history is being run, as you see here from the status bar. Once I get analysis done, then I can go ahead and view the results. The same options as we've seen before. You can go through the response history plots. In this case, I have different ground motions, so I can move through the different ground motions and the different response quantities. Now, if I click on Save Results, then it will save a single file for each ground motion containing the response, the associated response history quantities. So now, using the same definition in my project, I will change the system model from a linear elastic to a bilinear model. So I go ahead and define again the system model. I will choose a non-deteriorating bilinear system with symmetric response. I'll go ahead and click next. So this model is defined using basically two quantities: the elastic stiffness, which has been already defined in the SDOF module. The other one is the limiting or the yield force or the yield displacement, and the post-yield slope, Kp. You can change this, and once you change the value, this plot on the right will be updated accordingly. So I will put a limit on Fy of equal to 0.1 of the weight which has been defined in this SDOF, calculated as the mass multiplied by the gravity acceleration. For the post-yield slope, it has to be defined as a percentage of the elastic stiffness. For example, if I put 0, then this becomes an elastic, perfectly plastic response. Of course, because we have a P delta effect, then this 0 slope is being rotated by the amount of the P delta. For now, I'll just add 0. You can also add a limit on the ultimate displacement for this system, which I will not do for this analysis. Then I will go ahead and click submit. Now it tells me over here that the system model is now bilinear. So I can go ahead and run the analysis. So now the analysis seems that it's taking a little bit more time because now it's a nonlinear system. Once the analysis is done, again, we can look at the results. For the response history plots, same as before. If I look at the force distrum, you will see that in many cases, the force for many ground motion is being kept at the limit that we put, 0.1 of the weight. If you want to look at the response, we can go ahead and look at the force displacement response over here. So again, we see the backbone curve in black as well as the response of the bilinear system. In many cases, depending on the ground motion, sometimes it remains elastic, and in others you see different levels of plastification. Note also that for the different responses, you can zoom in. You can also inspect the value of data points on the graph to make sure that everything is correct. You can also save the current figure as a .png file. You can also print the current figure as a PDF file. So far we have covered linear and simple bilinear non-deteriorating systems, as well as how to define a single and multiple ground motions. Just for conclusion, in the ground motion module, we can also define a harmonic wave. This includes currently like 4 different wave types, like sine wave, cosine wave, triangular, and rectangular wave. For each one, you will need to define the amplitude in G units, as well as the period of the wave and the total duration. So for example, if I use cosine with a 0.3 G in amplitude and a period of 2 and a total duration of 10 seconds, I can submit this. Using the scope button, I can look at this wave. Again, it's a cosine wave that has a total duration of 10 seconds, a period of 2 seconds, as well as a maximum amplitude of 0.3 G. So this we can also see here for transform that shows a single spike at 2 seconds or 0.5 Hertz. I can conduct the analysis right away. I can view the results.